All right, so in this next section, that's a follow-up to 15.1, we're going to really talk about some phenomena that involve refraction. So last class, if you recall, we talked about the bending of light as refraction through some sort of material. And usually that material has a different index of refraction than air does, and thus you see the material. We showed that demonstration with vegetable oil and Pyrex that have the same index of refraction, and the light that's passing through the liquid as if it's not even bent at all, so that Pyrex glass or cup disappeared. So we're going to see in this lesson how there are certain phenomena that are very useful that we use for applications of total internal reflection. Okay? So let's take a look at this. So think about what we talked about the other day. When light enters another material from air, okay, it bends toward the normal. So here's what we have. In this diagram, normally the light should do this. Right? The light would continue, but when it hits the material, instead of continuing along this dashed path that it would continue along normally, it bends. And it bends toward the normal.
So that means it's going slower, right?
Correct.
So,
Yes.
I don't have my glasses.
Yeah. Okay, there's the normal right there in red. So instead of continuing along the dashed line that you see to the right there, instead of continuing along this line right here, this wave gets bent. It does not continue along this line, it bends toward the normal. Do you understand what I mean by toward the normal?
Yeah.
It should follow this line. Instead, it bends toward the normal. This is the normal. Now, it's trapped in glass for a second, and then it exits the glass, and instead of bending toward the normal now, it bends away from the normal. So we have a second normal to draw in, please. Every time there's a light passing through an interface of two different boundaries, there's another normal. Gabe?
The normal doesn't have to be horizontal, right? It just has to be perpendicular to...
The normal is always perpendicular to the surface, but it's, in this case, the normal occurs wherever this light ray intersects a boundary. This is a boundary here. There's an intersection right there. This is a boundary. The light ray follows and intersects right there. So wherever the light ray intersects a boundary, you draw a perpendicular line from. Okay? So yeah, as we can see, this light ray would really want to continue like this. Okay, if I continued from this bent ray right here, this bent ray would continue this way. But now, because it's entering air out here, it bends away from the normal. So what happens as a result, though? What happens as a result? What does it look like, at least?
Like when you have a glass and you put the straw in the glass and the straw is here and here and then when it's in the glass.
It's like shifted over, right? But you still see it because these light rays are parallel. Like this here. That's a terrible drawing, the first one, sorry. Are perpendicular to one another.
Those two lines are
Okay? Thank you. Parallel to one another, not perpendicular. We're using the word parallel so much with the normal. Those two lines are parallel to one another. So the light rays do reorient themselves when they come through. But what happens is we see that like staggered image to the left or to the right of it. Okay? Yeah, Chris.
It's not like when you're like underwater and you're looking up and things are like
Yep.
shifted over all over.
Exactly. Okay, it's like when you look in a glass of water and the straw is there and the straw looks like it's broken, or a pencil or whatever the object is. Okay, but the idea is that the image still appears, just shifted over, because these rays right here, right, these rays are really shifted over from one another. Now, what we want to talk about is focusing of these rays. These rays that pass through glass, as you know, when you look out the window, the building still looks the same. It doesn't look like anything changed because the rays might bend, but then they bend back, so you don't see that any change there. But if we want to change the direction of light, what we do is we use something called a lens. How many of you use lenses every day?
You want one?
You have contacts, your glasses?
I was saying.
Do I want one? No. Now, if you use your cell phone and use the camera on it, you use a lens every day also. Okay? There's a lens in the phone camera. Okay? So the idea of lenses has to do with concentrating or dispersing of light. So let's talk about the two different types of lenses that we're going to really focus on. First, it's not easy to draw this, sorry. Okay, like a convex lens. The idea behind a convex lens is that it takes the light rays and does what with them? What does it do with the light rays? The light rays enter like this. Okay, 3 light rays are coming through. It hits the lens. The lens might be in front of an eye or a microscope or something. What does it do? It's not a filter. It's not a filter.
It compresses the light.
Sure, it's a good word. Or how about converging? It converges the light. It causes the light to bend a little bit like this. And then it hits the second part of the lens, which is the other interface on the right side, and the light rays literally converge to a point. Okay, all the light rays focus on a point.
This is like a cartoon example, but when they show like satellite beams and like all the beams converge into one point.
Is that like shoots off some
Laser,
laser or
yeah.
something? Yeah, like a Death Star.
Yeah.
Yep. Okay? All these rays focus on one location, and this location is usually very important in the eye, in the human eye. We'll talk about how that's called the retina in your eye. It's where you focus light rays and you can change this. But the idea of a converging or convex lens, okay, a convex lens or a converging lens, is that the light rays focus at a certain location. We call that a focal point, similar to with an ellipse. Remember, the ellipse has 2 focal points. One was the sun and one was empty space. This is a focal point right here. What do you think the opposite of a convex lens is? Concave. Okay, and instead of converging the rays, what does it do to them? What's the other word then? Expand, that works. I heard expand, that's good. Separate, that works. How about the opposite of converge? There it is. Okay, we call this divergent, very good. This is concave, and it diverges then, or it's a diverging lens. The first one was a converging lens, the second one was a diverging lens. So things that diverge literally means separate, like many of you already mentioned. Light rays come in. They hit the first boundary. They hit the second boundary. And these light rays literally diverge. Okay? The reason this happens is because of Snell's law, because of refraction. Lenses are really just glass, but instead of being normal glass, what are they? Not material. Something else. Yes, they're shaped. Okay, they're shaped. It's glass that has been shaped. That's all a lens is, guys. Glass that has been shaped. So when you look at your glasses, if you honestly analyze your glasses, look at them. You'll see concavity in them. Do you see what I'm saying? Yeah, you'll see the lens is literally bigger. You'll literally see the lens itself here, okay, is a concave, and this is actually convex. This is a combination. We'll talk about that in a moment. We'll talk about farsightedness and nearsightedness. But this end is concave, this end is convex. Thank you for letting me touch your noses. Okay? Benjamin Franklin came out with what we'll call bifocals, which was different.
Oh, because he's nearsighted.
Yes, that was at the top and bottom half of the lens being split. So let's talk about application of them. 2 of them. I'm not going to write anything here. I'm just going to talk, so you want to write, okay? I'll zoom in on certain things and talk, but you want to be writing. So the first type of problem with seeing is called hyperopia. And hyperopia simply means farsightedness. How many of you have hyperopia? You have hyperopia?
Yeah.
What does that mean?
It means like farsighted.
What does farsighted mean?
It means I see better far away.
Yeah. So your glasses are for reading?
Not really. I don't think so. Because I can.
Oh, I'm
Take them off.
nearsighted then.
Can you read the board still?
Yeah. It's like,
Does it feel a little blurred?
well, yeah.
So it means you're probably not actually farsighted.
I don't know.
Well, my doctor says that I am. My dad is nearsighted. That's how we always compare.
Well, here's the tradition. I was expecting to know what there is a hand on it. Usually, younger people are nearsighted. A lot of younger people can see near, but cannot see far, so they wear their glasses. You are the opposite.
Yeah.
You wear glasses to see near?
Glasses.
Interesting.
I don't even read books.
You're like Benjamin Button.
I I like,
You ever seen that movie?
yeah.
Person lives his life backwards.
Oh, yeah.
Usually, younger people, you can't see far. So, like, Christina's wearing her glasses to see the board, right? So, you're normally, as young people, you're nearsighted. That means you can see near. If you're farsighted, which is this example, this is usually older people's eyes that turn into this. Okay, because they usually cannot see up close. They can usually see far. You're an old soul. I don't know. So here's what happens though, ready? Follow me, please, follow. The light rays come into the eye. They hit the eye. On the eye, there's a natural lens. Okay, you see this lens on the outside right here? Okay, this is your lens, and this is the image of your lens, or the illustration of it. It hits the lens, and it causes these light rays to focus. Well, where do they want to focus? They want to focus right here. Put a little X here or something. That's where they want to focus. That's called your retina. If the light rays focus perfectly on your retina, you have 20/20 vision. And this is, again, assuming that we're looking for either farsighted or nearsighted. You could technically be both, which is weird, but usually it's a combination of that and, what's that called? Astigmatism? Right? Your eyes a little bit, one of your eyes better than the other?
My left eye a lot
Yep.
better.
My brother is the same exact thing. His right eye is astigmatism also. He will literally, if he closes his left eye, he has a lot of difficulty seeing with just the one eye. Now, you know what's interesting?
You should become a pirate.
You're a lefty in baseball. That's very difficult. How do you see? That's so difficult. I never realized that until now. Oh my gosh. You're not a switch hitter, right? You can't ever hit on this side? One day maybe try. It's got to be so hard to see. Because you see with your front eye when you're in baseball. Right on this side, I'd be seeing with my left eye. It's so difficult. Okay. We're going to think about that. Maybe, can you wear glasses that correct that or no?
I have contacts.
And they correct the astigmatism?
Yeah.
Okay. So maybe not. But, you know.
Isn't there something in your eye called refractory nerve or something?
Oh, what?
There's something called a refractory nerve somewhere in your
It's
body.
very possible. I don't know about it. It's possible. Maybe it refracts the rays of some sort. But if it's a nerve, I wouldn't think it'd be refracting. But it's very possible that it exists. I don't know. Google it.
Sorry.
Now, the idea of this is that the light rays focus, right? Here's how you remember. They focus too far from the lens. Easy way to remember, right? Mnemonic devices are things that help you remember. So when I see the word farsighted, think of the word far. Far means that you can literally see far. Okay, you can see far, you cannot see near. Okay, you cannot see, whoops, I put seer. I put see near together. No?
Yes, I get it. Whoa, that's aggressive.
Now, the light rays focus, what's that? The light rays focus too far from the actual lens. So what do you need instead to fix this? Give me more, not concave, convex, give me the other terms. You need a converging or diverging lens.
Converging.
Why converging, Dave?
Because you need them to converge closer.
Sooner.
Sooner, yeah.
Very good. You need a converging lens to fix this. Because the light rays need to focus a little bit earlier. So let's scroll to the right and take a look. Or pan to the right and take a look. And now we can see the difference. Look at the two eyes. The one on the left over here, we're noticing has just the normal lens of the eye on it. This one does also. But look right here. This is a converging lens right here. And this converging lens is exactly what Miles is wearing right now. This is not convex or concave, it's both really. Okay, this side is convex and this side is concave. So it's a combination of those two, but it creates a converging effect which causes the light rays to focus not out here where it was earlier. Remember earlier it focused beyond the eye, beyond the retina? Now it focuses a little bit sooner, and as a result it ends up on the retina. What do you think happens with nearsightedness? Yeah. And so what do we do to correct that? The opposite. Okay, that's all it is. So if you can remember how one of these works, you'll remember the other. Here's nearsightedness. I remember it by thinking the light rays focus too near to the lens. Right, here's the lens. Oops. Here's the lens. These focus too close to the lens, or too near is not really probably proper, but too close to the lens. So we need them to focus out here. So we need to diverge them a little bit so that when they converge, they end up at the right spot, right here. So we need to diverge them a little bit. So what you see is the light rays, when they pass through this lens, diverge a little bit and then come back and end up on the retina. Okay, the lens looks very similar, obviously, itself. But one is a converging lens and one is a diverging lens. Now, based on your prescription, what do you think changes? What specifically? You need geometry. Yeah, the curvature, the angle of curvature there. That's what's changing. Okay? How concave, how convex. You might call it the eccentricity of the curve, like we use for ellipses. Eccentricity is a term you could use. But the curvature is what's changing to correct it. This is called myopia, by the way, myopia. Okay, again, most young people, okay, can see well near but not far. Most young people, most of you, are nearsighted. Okay, except for our two exceptions that we already mentioned there, yes. All right, take a look now at an application of refraction that is not as simple as what we saw a moment ago. Okay, the one we just did is pretty easy. It's pretty straightforward. Here, though, something else is happening, a little bit different. Let me explain this. And this is difficult to visualize. I used the video last year. Unfortunately, for some reason, it was like an MIT video. They do a lot of MIT physics courses. There's one that was recorded, but it's been taken down. So I had to deal with that for the other class. So we'll discuss it, and then I'll show you at the end another simulation of what I'm talking about. So imagine a light ray hits a surface at 90 degrees. It just passes right through the surface. And we talked about that the other day. If it doesn't hit an angle, it's not going to get bent. If a light ray hits a surface perpendicular, it's going to go straight through. Now, if you look at a glass of water, are light rays hitting that perpendicular? Definitely not, because the glass of water is curved, isn't it? The glass itself is acting like a lens. It's curved. A window, though, when the light hits the window, it's pretty much coming through at a 90-degree angle when the light comes through. So you don't see that curvature. You don't see any change there. You don't see a distorted figure. Okay, nothing's being refracted, really, through glass panes that are straight, that are hitting at 90 degrees. If I take a light, like a laser, and shine it at an angle to the light, or to the boundary, obviously it's going to bend, because it's at an angle. Okay, yeah?
Sunglasses? Like,
They're curved.
the design, does that change anything? Because they're trying to stop the sun from coming in?
I mean, no. I don't think the curvature of the lens there has to do with refracting of the rays. They have to be parallel for you to see, or else it's a prescription then.
Okay.
So yeah, the curvature does not affect that. If you buy prescription sunglasses, you can get them to work that way. Yeah, but they are bent, but it's not to bend the light you would think with glasses that way. Not to like change the orientation of the light to focus it on a different spot of your retina. So the first image is this, okay? So please, this is sample 1. These are all samples. Put numbers next to them if you have to. Because the other class I remember last year got confused. This is scenario 1, scenario 2, 3, 4, and 5. So these are 5 scenarios. So imagine I am sitting here with a laser pointer, okay? I'm holding the laser pointer right here. And here's a little beam coming out. And the green, usually they're like green or something else, right? Here's the laser pointer. They could be green or red or whatever. Okay, the green ones go further than the higher frequency. Sometimes. Okay? So, yeah, and by the way, you could Google this. The different colors of the lightsabers in Star Wars indicate different things. It's kind of cool. Fun fact. But anyway, so I've got a laser pointer. You shoot the laser, it goes through the water, it hits the boundary between the water and the air, and it goes right through. So imagine this laser pointer is inside of a fish tank at the bottom. Right? Think about that for a second. It goes through the water, and then it goes into the air. Now, I take that laser, and it's on a pivot. So imagine the laser is on some sort of a pivot, like we talked about with torque. There's your pivot point. And now you rotate the laser. All right? You rotate the laser. I'm going to rotate it, but I'm also going to kind of move it over. Okay, for the sake of this example. But imagine it was on like a pivot. You could just rotate the angle. Now the light ray will bend due to refraction. Why is it bending away from the normal, right? Look, I'm going to zoom in. I'm going to zoom in for you. Take a look right here. Follow. Here's the light ray. Here's the light ray. It hits this interface right here. Here's the interface, right? Here's the normal. I don't even have to draw it. There's the normal. Remember, look, there's 1, 2, 3, 4. There's a fifth one. There's 5 normals. For every different scenario, 1 through 5, there's a different normal. Keep that in mind. Here's the normal for this one. The normal is drawn in for this angle, and I'll explain why in a moment. Here's the normal right here. So if you want to, you can draw a normal in blue or something else if you'd like. Here's the normal. Well, what happens? Why does it bend away from the normal? It's going faster. And when light speeds up, we talk about how it bends away from the normal. So this light ray should really, this laser, should do this. Follow, please. Ready? It should do this. It should follow that trajectory. But it bends, instead of going here, it bends away from the normal. And we know that. We've already talked about that. Now here's the thing. This is where it gets really cool. If you continue to increase the angle of incidence, it affects the angle of refraction also. So now I set up a laser over here that shoots a laser. Watch, ready? I should use the lightsaber actually for this one. That's the sound of the lightsaber. So I shoot the laser, and now it follows along this path. It's a perfect pitch. Look at that. Like perfect angle, isn't it? It's like a perfectly linear function on top of the other. Wow. So the light ray continues, goes like this, hits this boundary, and then it gets refracted further. I can't use the light ray anymore because it's going to be misleading. Sorry. So then it continues, so the light ray continues like this, hits the boundary, and gets bent. Eventually, as this angle of incidence right here, here's the angle of incidence right there. See where I'm pointing? There's the angle of incidence from the previous one. There's my new normal. Right, there's my new normal. So here's my new angle of incidence right here. Notice, this angle of incidence was very small. It got much bigger. It got even bigger in the next example. When the angle of incidence increases, we know that the angle of refraction increases. We can see that from Snell's law. Eventually, though, this light ray bends enough until it bends even further from the normal. Look how big this refracted angle is now. It's very large of an angle compared to this. This was a smaller angle. It gets bigger until what happens? It hits this and it bends so much that it goes along the surface of the water. The refracted ray doesn't even escape the water. It kind of glows along the top of the surface. And you could try this actually if you have a fish tank at home. Extra credit. Okay, if you have a fish tank at home, you want to try it. If you don't, what you can do, honestly, what you can do is you need some sort of a clear rectangular solid, just fill it with water. It doesn't have to be an actual fish tank. It can be something like this big. You could use something that's like a Tupperware, but it has to be perfectly clear for this to work well. Okay? Now, your enclosure, fish tank enclosure, could work very easily if you turn off the light and you use a laser. And you'll see it. You'll literally see the laser go like this, and it'll come out. Then you'll see the laser bend, and it'll have like a little green like sheen, a little light on the surface. It'll just glow on the surface green. Until what happens? The angle gets even bigger, and then the light gets bent from the normal. Right, here's the new normal. Look at the normal out here. Well, look. This light ray, instead of continuing where it should, like that, it gets bent back in, like that. So here's now, let me erase what it should be like. I'll erase that. Here is the new angle of refraction. Look at that. The angle of refraction is greater than what in that diagram?
90.
Greater than 90. When the angle of refraction is greater than 90, it literally bends back into the surface, into the material. It looks like reflection, actually. It's not reflection. It looks like reflection, though. It looks like it's hitting a boundary and getting bent back in. Okay, it looks like it's hitting the boundary and reflecting off the surface. But it's actually bending so much that it bends back in. Okay, Chris?
Is that why like full lights are curves? Like the lights in the pool?
That's to disperse the light, actually, really. That's the boundary of it, you mean? Like it's like a concave on the inside, convex on there. That's really to disperse the light. But it probably hits the surface at an angle that causes that glow at the top. There is application of this in a pool, but I think the curvature is more to disperse the light. But I could see this being part of it. And behind the light, there's usually a lens on the back that causes dispersion also. But yeah, usually you'll see this in a pool. You'll see a glow along the surface at the top of the pool. It's total internal reflection causing the pool to glow. It's called total internal reflection, even though it's refraction. Okay? It's called total internal reflection. It's a phenomenon that we've discovered. And it's really because of refraction though. And the whole idea is this. Ready? When the light ray gets bent enough, I should use a different color for this. Can I do that? No, it's only, here, I use the green. There we go. When the light ray gets bent enough that it bends out, it bends back to be 90 degrees. Right, here's the refracted angle. Look, 90 degrees right here. Angle of refraction here was like, say, 40, 50, 90, maybe like 120. The refracted angle is increasing, we could see. When the refracted angle becomes exactly 90, you begin to exhibit total internal reflection. And the light ray kind of just goes along the surface. As soon as you increase the incident angle a little bit more than what we're going to call today the critical angle, beyond the critical angle, every light ray will bend back in.
Wait, so just clarifying, the angle of incidence decreases or increases as the refraction?
They're both increasing. That's the whole idea. Ready here? Let me show you. Ready? This is the angle of incidence first. Then the next angle of incidence. Then the next angle of incidence. Then the next angle of incidence. You see those angles are all increasing? This is the smallest, this is bigger, this is bigger, this is the biggest angle of incidence. As the angle of incidence increases, right, we eventually get to what we call the critical angle. And we're going to actually rename the angle of incidence critical at this point. And we'll say any angle beyond that exceeds the critical angle, so we get this internal refraction or reflection. Okay, it is refraction now. All right, let me show you a quick mathematical proof of this, and then we'll get into an example. So we see that this happens when the refracted angle becomes 90. That's what we saw a moment ago. So write out Snell's law, please. Okay, write out Snell's law. Now, let's go ahead and plug in 90 for theta r. Plug in 90 degrees for theta r. What's the sign of 90? 1. Okay, so it doesn't matter. Put a 1 in its place. So we get this. Now, as a result, we could figure out what the angle needed of incidence is to cause total internal reflection by solving for theta. It's so nice. It drops off. This goes to 1. Just put a 1 in its place if you have to. Solve for theta I now. Solve for theta I. How do you get theta I by itself? How do you get theta I by itself? How do you get theta I? What do you do to isolate it? Oops, I'm drawing on here, not even meaning to. I thought I was on the grab tool, sorry. There we go. Only Siobhan knows how to solve for theta I? Chris?
Divide by NI.
All right.
And inverse sign.
Inverse sign. Okay, this will always work to give you sine inverse of NR over NI. Now, write down this little asterisk at the bottom, and you could prove it to yourself, actually. You can prove it to yourself. NI must be greater than NR. NI must be greater than NR. Because we want the denominator to be bigger than the numerator here. And you'll learn more about this year in your Algebra 2 trig class. Okay, you'll learn all about this idea where you cannot have a sine function that exceeds 1 ever. So if you tried to do sine inverse of like 1.2, it would not work. You'll get an error. So again, the denominator is always going to be bigger than the numerator, which means that we're going from some material that's slower to some material that's faster for this to happen. You have to go from slow to fast for total internal reflection to occur. The boundaries, okay? And if you go back to your last slide, please. What material did you go from? From water to where? And isn't water the slower material compared to air? What's water's index of refraction? 1.33. And air is only 1, right? So you get the sine inverse of 1 over 1.33 to figure out the angle needed to get total internal reflection when going from water to air. So based on the materials, the angle will change. Now, that's why we talked the other day about the idea of diamond and why diamond sparkles. When light rays get trapped inside of a material, it starts to sparkle, it starts to give off light. So the angle that we need for diamond is a certain value. Diamond sparkles a lot because of its end value. Think about it. Ready? Hold on one sec. If I wanted to figure this out for water and air, right? Here's what I've got. These are the values for water and air. We've got 1.33, and we've got a 1. Now, if I change, instead of water, if I change it to diamond, here's what it does. Calculate those numbers, please. Calculate those numbers, please. Sine inverse of 1 over 1.33, sine inverse of 1 over 2.4. What do you get when you calculate these two numbers?
That's why the cut of the diamond is really important.
Yes, has to do with the cut, absolutely. When they cut diamonds, they're cut a certain way to attain these angles, yep. And you've ever seen a diamond shape, the whole shape to it and everything. That's why, by the way, if you discover, if you found a diamond that was really small, and it's not, you can't cut it, it's not worth anything. Only big diamonds are actually worth a lot. I've been diamond digging before, believe it or not, I have. True story. One of my buddies was getting married, and instead of doing a traditional bachelor party, he wanted to go camping and hiking or all the outdoor stuff. So we went diamond digging. He had a new dog. The dog was 5 months old, and it's a dog that was made to dig, a dog that's made to hunt on farms and stuff, that's grown that way or breeded that way. So we brought the dog with us. We went camping for the whole weekend, and we went diamond digging to find a diamond for his wife for her engagement ring. He ended up finding a really, really small one that he ended up just mounting on a pendant and giving to her. Because it couldn't be big enough to be cut. A diamond that has to be cut has to be big. It's not a small little piece of a diamond. It's not worth anything. Anyway, what are the angles? What do you got, Sam? Give me one of them. Are you in degree mode or radian mode, though? What are you in? Hit mode. There's a mode button, right? Is degree or radian highlighted? I see radian. Go over to degree. Go down, go to degree and hit enter. Quit. Second quit now. And then press second. Enter. And do it again. There you go. See how the answer is different? Okay. All right, so Sam's got the one. Sam's got diamond. What was diamond, Sam? All right, there's diamond. Chris. First one, Chris. So take a look. Take a look, guys. Come on. Refocus. Refocus. For water going to air, the angle has to be around 48 degrees. 48 degrees you have to be at for this to cause total internal reflection. But once the light ray goes into the diamond, this is absurd. Once the light ray goes into the diamond, it only has to hit at an angle of 24 degrees, or in this case, this is the critical angle. Any angle that exceeds that, anything greater than 24 degrees, will cause internal reflection. So for a diamond, if it hits at 25 degrees, 26 degrees, 27 degrees, the light will be trapped in there. And the diamond is shaped in a way so that it traps the light, it sparkles. Okay, for that specific reason. Okay, so what we're going to see here is that total internal reflection occurs differently for different materials. What do you got? For the top one?
No, for the bottom one.
I might have copied it wrong. What was it?
42.97.
For diamond?
Yeah. No, it says 0.4. Yeah, 0.4.
I got 24.6 for sure. Hit mode. Are you in radian or degree? Yeah, there you go. Okay, go to degree, guys. Come on, go to degree. Well, whatever. Check anyway,
So it
okay?
has to be at an angle of
No, in order to stay in.
In order to stay in.
Remember, this is the angle. This or more causes internal reflection. This or more. So for water, if you go home, honestly try it. Seriously try it. If you go home and try this, if the angle is more than 48 degrees, it will, the laser will stay inside of the water. It really will. It's kind of cool. Okay? And that's the video that unfortunately is no longer available. I can try and find another one once we have time when you're working on the lab in the second period. Okay? Okay, this next example we just did, so you don't have to redo it. But if you wanted to see the solution for it, the idea is to start with Snell's law again. Right? Ni sine theta I equals Nr sine theta R. Or you could go right away and put a 90 in here for theta R. Because that's what you're looking for. You're trying to find the critical angle. The critical angle occurs when it's refracted by 90 or more degrees to cause it to bend more than 90 degrees back into the substance. So you could always set that equal to 90. And you'll always get that answer that we got a minute ago. This was the answer we got a minute ago. Sine inverse of NR over NI. You're always going to get this answer whenever you plug in 90 for theta. Well, we're going to call this another formula. Call this the critical angle formula. Okay, that's what we have. I think it's on your formula sheet. Take a look, please. It should be on there. So you have Snell's law, and then whenever you set theta R equal to 90, okay, we're going to come up with this critical angle formula. So all you have to do ever is plug in. Now, you know what? You know what makes this section so easy mathematically for you on the test? If you mix these two up, what's going to happen on your calculator?
Error.
So if you get an error, what should you do? Probably switch your NI and NR. So it's a very easy way to check. You almost can't get it wrong. You can't come up with the wrong answer unless you just literally plug in the wrong numbers altogether. But if you switch the numerator and denominator accidentally, it'll say error, just switch those values. Okay? You're always given two materials, always.
It's always going to be 90.
Yeah, whenever you're finding the critical angle, theta R is 90 or greater. Okay? Take a 2-minute break, then come back. Keep your notes open. When you come back in, grab a laptop. Okay, when you come back in, grab a laptop. Keep your notes open though. An application of this idea is called total internal. An application of the idea of total internal reflection is called fiber optics. There you go. Okay. So fiber optic cables. Fiber optic cables use what are called light pipes. You really have several notes here, right? They use what are called light pipes. That's what these are. Okay, if you've ever seen these before, like a carnival or a fair?
Oh yeah.
Okay, you know what these are? They're it's almost like a ball with all these little things coming out of it, and at the end of it, there's this little light.
Oh, it's so fun.
But actually, throughout the tube, you don't see any light. It's really cool. Here's what happens. The light rays go in at an angle, or they hit the actual incident surface at an angle greater than the critical angle. So let me, what?
Is that a finger or
Yes, I'll zoom in a minute. So the light rays enter this light pipe, and they hit the surface right here, where they want to leave, right? These light rays want to do this, ready? They want to go like that. But they don't, because the angle is greater than the critical angle. So they bounce off. And then they bounce off again, and then they bounce off again. And the light signal literally travels through what's called a light tube. And at the end of the light tube, you literally have these things. Okay, that's a person's finger there, yes. So the light tube ends are all these bright dots. See them all? But look at the actual tube itself right here. You don't see any light on the outer part, only at the end. It literally like traps light and causes it to come out another end. So it's an amazing phenomenon that enables us to use fiber optics. Without it, we can't. High-speed transmission of signals. I'm trying to think of another application before I go further if I want any more. No, okay. The layout is called dispersion. And we've actually already alluded to this. We've alluded to this already. And we've talked about the idea that light rays, like the visible spectrum is white light that can be broken into its colors. That's what a prism does for us here. Okay, so dispersion is refracting light, but in a way that it separates it into different components of wavelengths. So the red wavelength, the blue wavelength, the yellow wavelength, they're all different wavelengths and frequencies, which we know are inversely related. Okay, they're all different. And as a result of hitting this boundary at a certain angle, it bends once, and then it bends again. And it exits the prism with different colors of light. Okay, you can see this on any prism. Even glasses, watches, you see rainbows appear all over the place. It's just the dispersion of light. That's all it is. A rainbow itself, yep? Okay? Anyhow, that's it for this last year homework for this, okay?